Yeah, so the next speaker is Zoe Hitzig, who's a PhD candidate right now at Harvard, and so she's going to tell us about her work on contextually private mechanisms. So yeah, take it away.
Thank you so much. I'm super excited to tell you about this joint work with Andy Haupt, who's a graduate student at MIT, who's over there. Roughly speaking, what I'm going to be talking about today is a privacy-related desideratum for mechanism design. And what we're going to study in this paper is which common mechanisms can be implemented in a way such that the designer only learns what is strictly needed about the agents to compute the outcome of the mechanism. And to motivate this idea, let's start with one of EC's favorite topics, which is Google's ad auctions. As many of you know, Google for a while was using second price auctions to sell its advertising slots. We all know various problems with the second price auction. One of them that came up in the recent lawsuit led by the state of Texas was pretty interesting. And this is, so one of the legal filings alleged this. Google induced advertisers to bid their true value only to override preset floors and generate unique and custom per buyer floors depending on what a buyer had bid in the past. So our diagnosis of what's going on with the second price auction, or what is alleged to be going on with the second price auction in this case, was that Google, the designer, learned something about participants that it didn't need to know. It did not need to know the losing bids of advertisers. And it learned this and used those bids against them in the future. So we're going to propose this concept that says, essentially, the designer should not learn too much about participants. And there may be various motivations behind this idea. One might be that there's limited trust in the environment. Participants or other third parties have limited trust in the designer's ability to stick to its word, or privacy might be valuable in itself. And the main features of the setting that we study here are first that we're going to look at dynamic implementations, and we need dynamic implementations because that will allow us to talk about partial revelation of agents' private information. So we can talk about the designer gradually learning subsets of the agent's private information. The second key feature of the environments that we'll study are that we're going to focus on environments where there are pretty severe restrictions on what the designer can do. And those restrictions reflect our interest in understanding what can be done with fairly primitive technologies. What kinds of privacy can we guarantee when we're only using primitive technologies? And of course, as all of you are probably thinking, if the designer has access to advanced cryptographic techniques, then there are much better privacy guarantees that they could get by using, hash functions or zero-knowledge proofs and so forth. So our setup starts off pretty basic. We have n agents with private information, which we'll encode in a type profile, bold theta. There's some set of outcomes, x, and there's some choice rule that the designer wants to implement, which we'll call phi, which takes private types and maps them into outcomes. And these primitive types of protocols that we'll focus on, at least at first, are essentially, you can think of them like extensive form games with direct revelation and perfect recall. And in these extensive form games, one agent is called to play at a time, and they're asked a particular kind of question. They are asked about whether their type falls into some subset of the type space. And more formally, we're going to model this extensive form game as a directed rooted tree where each node V is labeled with some subset of the full type profile, which we'll call bold theta V. And each edge is labeled with an agent. So if there's an edge from node V to node W labeled by agent I, it means that the type space associated with node W is a subset of the type space associated with node V, and these two subsets differ only along the dimension of agent I. So that's capturing the idea that the designer only learns about one agent at a time. So just to enforce this, here's a simple example. 2 agents, 2 types. We can visualize this as a square up here. At first, the designer has the full type space as possible. And then after asking a question like, is agent 1's type A, the answer, yes on the left or no on the right, reveals, sort of brings the designer to a subset of that, a proper subset of that type space. So now we're ready for the key definition of this talk. We'll say a protocol P is contextually private if, for all type profiles at distinct terminal nodes V and V prime, which only differ along the dimension of one agent, lead to different outcomes. So one way of thinking about this is if the designer can distinguish between type theta I and theta I prime, holding everyone else fixed, then it must be that the designer needed to know that agent I was not theta I prime and was in fact theta I, in the sense that if they hadn't known that, the outcome would have been different. So then we say a choice rule phi is contextually private if there is a contextually private protocol P that implements it. And notice here, in this definition of contextual privacy, the set of admissible protocols might play a role, though we'll talk mainly about the types of protocols I've defined so far. And we call this contextual privacy because it is a type of privacy that depends on context. It depends on the choice rule. So different sorts of information can be revealed or are allowed to be revealed depending on what the choice rule is. So all information is not treated equally in this type of setting. So this is a good time to give an extremely abbreviated literature review. The most closely related idea that we draw on in this paper comes from the old cryptography literature. There's an idea that was publicized and discussed a lot by Benny Chor and Eyal Kushelevitz in the late 80s and early 90s, and then adapted into auction and social choice settings by Brandt and Sandholm about a decade later. And what this idea is, it's variously known as full privacy or unconditional privacy. And this idea is defined on decentralized protocols. And so it says roughly if there's some function f that you want to compute, and you need to compute it using information that's distributed throughout a bunch of different agents, can you implement or can you compute that function without revealing any more information than is contained in the outcome itself? So it's a very decentralized idea, but has a similar flavor to contextual privacy. And in fact, part of what we do here is import that idea into a canonical, centralized mechanism design framework. I'll also mention a variant of unconditional privacy that's used by Paul Milgram and Ilya Segal in their work on spectrum reallocation and clock auctions, which is called unconditional winner privacy, which is unconditional privacy just for the winner. We can talk more about that in the questions if desired. So there are 2 sets of results that we want to highlight today. The first is that when we restrict our designer to using the kinds of protocols that I defined on my model slide, contextual privacy turns out to be a very demanding desideratum. And then we'll show that once we allow for just one more kind of query and expand the designer's scope just a little bit, many things become contextually private. So most of the impossibility results that we present in the paper rely on this neat lemma called the corners lemma, which appears in this earlier cryptography research. And it's a very powerful idea and can be thought of as a kind of minimal counterexample. And if you can find a counterexample like this in some choice rule that you're trying to figure out, and you're trying to figure out whether it's contextually private, then you've gotten your answer. So the idea roughly is, let's focus on two agents, I and j, and forget about the rest of the agents, hold their type profile fixed. It must be the case that if the choice rule leads to some outcome x for type theta I and theta j, and single deviations from theta I, theta j also lead to x, then it must be the case that the double deviation of theta I and theta j to theta I prime and theta j prime also leads to x. So it's called the corners lemma because of this picture here, where if we visualize theta I, the two possible types for theta I and theta j as a square, then it must be the case that if these three boxes lead to the same outcome under phi, that y also leads to that y is equal to x. And so with this tool, we're able to show that the second price auction does not have a contextually private implementation, nor does a Walrasian auction, nor does any stable matching in a matching domain, nor does any efficient and individually rational assignment mechanism in a housing assignment domain. And I don't have time to go into the proofs, obviously, but you can see that basically for each of these, we use the corner lemma. And we're able to sort of deploy it in all these different contexts. The good news in this first setting is that there are two common mechanisms that are contextually private. The first is a serial dictatorship, and the second is a first price auction. And the first price auction is contextually private when it's implemented with a descending or Dutch auction protocol. So the second set of results, as I mentioned, sort of expand the designer's toolkit in the following way. The designer is now able to additionally use counting queries, which essentially ask how many agents types satisfy a certain property. And crucially, the designer is able to learn just a number, how many agents types satisfy this property, without learning which agents satisfy that property. And so this turns out to be really powerful, and I'll talk about why this works for the second price auction. In fact, the second price auction now, with this kind of counting query, can be contextually privately implemented using an ascending auction protocol. And we're going to have to assume a condition that's much weaker than a no ties condition, which essentially says that there can't be two agents that have the highest type. And we can discuss, if we have time, we can discuss that condition in more detail. In the newer version of the paper, not the EC version, we also showed using a similar condition that the deferred acceptance choice rule has a contextually private implementation under counting queries. So just to give more of an idea of how counting queries work and why the second price auction is contextually privately implementable with an ascending protocol, let's first imagine a counting query of the form. Well, let's imagine that we have a true type profile as shown on the upper left. Agent 1 has value 1, agent 2 has value 2, agent 3 has value 3. Now the designer asks, how many agents have a type above 1? And the answer to the counting query is 2. Then the designer asks, how many agents have a type above 2? And the answer is 1. And now the designer has enough information to know, A, the price that should be paid, that it is 2, but it still needs to know which agent had the highest value. And so now it can use an individual query to go to each agent and say, is your value above 2? And when it does that, agents 1 and 2 say no, agent 3 says yes, and in the end, the designer knows what is shown on the right about the type space. And notice that the designer does not know anyone's type exactly. It only knows that 1 and 2 have values either 1 or 2, and agent 3 has value either 3 or 4. So contextual privacy is satisfied for the ascending auction protocol. And I won't have time to talk more about this condition, but I will end by mentioning some interesting connections. When counting queries are allowed, we find that all of these different choice rules have contextually private implementations. And what's sort of interesting about these implementations is that they're all sort of like tâtonnement in a way, in the sense that they are sort of estimating demand in some sense, and then the individual query is used to figure out who gets the allocation. Interestingly, even with counting queries, contextual privacy is not fully permissible. For instance, we show that the top trading cycle's choice rule doesn't have a contextually private implementation, even when we allow for counting queries. So I'll end there. Here's a summary. Excited to hear your questions and thoughts.
So, well, yeah, you know the drill. If you have any questions, now is the time to ask them. We can take 2-3 questions right now. Yeah.
Yeah, really interesting. I had a question about kind of the robustness and ways to get around. So you had this slide up, I think 2 or 3 slides ago, with the example of second price auction. Mm-hmm. And so this is not really the counting query method, but could you imagine the following thing, which is, look, I'm going to get around this need for contextual privacy by just saying I'm going to charge just everyone 1 cent if agent 1 gets it, 2 cents if agent 2 gets it, and 3 cents if agent 3 gets it. And I think that gets around your definition, right? Because it's technically a different outcome for every one, but it's not going to change the bidding strategy.
Absolutely, and that's where it's sort of tricky to come up with full characterizations here. So far, our first attempt was to understand which common mechanisms that we see in the real world have contextually private implementations, but you're absolutely right that sort of pathological auctions, like the one you described, exactly. And I think that sort of introducing statistical queries will also complicate our definition, because if in a similar vein, if you introduced some randomness and said with probability epsilon, this is the outcome, then lots of things will be contextually private. And so we think that if in an extension that allows for that kind of choice rule, we'd also want different protocols, statistical protocols, and a statistical notion of contextual privacy that would then also be interesting to compare to differential privacy. Yeah. Yeah.
Also related to this example, so I really didn't need to know that 2 agents or say 3 or 4 agents had the lowest type, as long as that was greater than 1.
Exactly.
So somehow like this like 1 agent at a time notion is making this contextually private despite this. I guess 2 questions. Can you relax the 1 agent difference at a time thing, and can you replicate your results with, say, greater than 1 like threshold type queries that would allow you to, I think, truly not learn anything more than you needed in this case?
Yeah, that's a great idea, is to add for a kind of even more general kind of threshold query. I think the hard part would be knowing when you have a type profile for which you can always compute the second price outcome, because there might be some type profiles here for which you you wouldn't be able to use that method, I think. But maybe I've misunderstood.
Just like keep increasing this price until it goes to exactly one person, at least this price. I think that would work, just for this second price. I don't know about the other mechanisms, but.
Interesting. Yeah, thank you for that.
All right, so it's like 5:56, so I guess maybe we should, go to the next speaker, but thanks a lot for a great talk, Zoe.